starting with the name of Allah, who is the most beneficial and the most merciful. Dear fellows, Assalamu alaikum. My name is Abdullah. My resource person is Dr. Hammad Majeed. My student ID is 23011068004 and my program is BS Physics. The topic of my presentation is photoelectric effect. First of all, we will discuss some of its contents. We will discuss the introduction, light and photon, the discovery and the history of photoelectric effect, its process, its experiment, the view of Albert Einstein, the photoelectric law, and the minimum conditions that are required for photoelectric effect, and the factors which affect it, and some of its applications. Dear fellows, when we first time hear the word photoelectric effect, the first thing that come in our mind is what does that word mean? So I will tell you what it means. The photoelectric effect, it is a phenomena of the emission of electrons when a light that have certain wavelength and certain frequency, it falls on the surface of metal. This is called as photoelectric effect. Those emitted electrons, they are called as photoelectrons, and this phenomena is also called as photoemission. The current that flows due to those photoelectrons, this current is also called as photoelectric current. In order to understand the process of photoelectric current, we must know about light and photons. What is light? Light, it is defined as electromagnetic radiation that have wavelengths in between 380 to 750 nanometers that are visible to human eye. What are electromagnetic radiations? Electromagnetic radiations, such as light, they are generated by the oscillation of electric and magnetic field, which means that they are also produced by heated molecules or electrons. Some of the examples of the objects or the materials that produce electromagnetic radiation, they are incandescent lamp, whereas and the fluorescent lamp. The electromagnetic radiation, they extend from gamma rays and X-rays through to the radio waves and to the long radio waves. Each rays, they have its own specific frequency and specific wavelength along with its specific energy. The electromagnetic spectrum. The following diagram, it shows the visible spectrum as well as the ultraviolet and infrared radiations. This diagram, it shows whole the electromagnetic spectrum along with its specific frequency and its wavelength. Photon. An alternative physical description of a light is to consider radiations as being emitted as discrete packets of energy. These discrete packets of energy, they are also called as photons. They have dual nature, which means that they have characteristics of both particle and a wave. This fundamental parameter that distinguish one part of the electromagnetic spectrum from another, it is the wavelength. What is wavelength? Wavelength, it is the distance between two consecutive crusts or two consecutive troughs. Photon energy level, they are determined by measuring their wavelengths. These wavelengths, they are expressed by Greek letter lambda. Of the two waves that are shown below, the left one, it have a higher wavelength that is 2 times longer than the one shown on the right. These two diagrams, it shows the wavelength of two different rays or two different photons. The first photon, it have larger wavelength as compared to the second one. The energy of the photon, it is directly proportional to its frequency and it is inversely proportional to its wavelength, which means that the photon that is shown in the first diagram, its wavelength is greater, so it means that its energy, it would be less as compared to the second photon. Properties of photon. For a photon, all the quantum numbers they are zero, which means that its magnetic, its azimuthal quantum number, etc. they would be zero. A photon they does not have any mass or charge, and they are not reflected in a magnetic and electrical field. The photons they move at the speed of light in empty space. During the interaction of matter with radiation, they behave as it is made up of small particles called photons. Photons, they are virtual particles. The photon's energy, it is directly proportional to its frequency and it is inversely proportional to its wavelength. The momentum and the energy of photons, they are related as the following expression. Energy is equal to product of momentum and speed. Planck's view. Planck, he was one of the first scientists who says that energy is emitted or absorbed in terms of discrete packets, which he called quanta. The energy of photon, it is directly proportional to its frequency, and it is inversely proportional to its wavelength. Frequency. Frequency, it is measured in cycles, which we also called as wave peaks per second, and it is expressed in hertz. The formula that Planck's calculated for calculating the energy of photon, it is E is equal to product of Planck's constant and its frequency, where H it is Planck's constant. Now Planck's constant, it is the smallest constant and its value is 6.667 multiplied by 10 having raised power minus 34 joule seconds. Now we will discuss the discovery and the early work of photoelectric effect. The photoelectric effect, it was discovered in 1887 by German physicist Heinrich Rudolf Hertz. In connection with work on radio waves, Hertz observed that when UV light shines on two metal electrodes, having a voltage when a voltage is applied across them, the light changes the voltage at which the sparking takes place. This relation between light and electricity was clarified in 1902 by another German physicist, Philipp Lenard. He demonstrated that electrically charged particles they are liberated from a metal surface when it is illuminated, and that these particles they are identical to that of electrons. It is also discovered by Joseph John Thomson in 1897. Further research showed that the photoelectric effect, it represents an interaction between light and matter that cannot be explained by classical physics, which means that classical scientists, they always thought that light, it behaves as wave. One inexplicable observation was that the maximum kinetic energy of the released electron, it do not vary with the intensity of light, but it varies with its frequency. The light intensity, it did determine the number of electrons released from the matter. Another puzzling observation was that there was virtually no time lag between the arrival of radiation and the emission of electrons, which means that this phenomenon occurs in no time. Explanation. The photoelectric effect, it cannot be explained by considering light as a wave, as I talked earlier. However, this phenomena, it can be explained by the particle nature of light, in which light can be visualized as stream of particles. These small particles, they are called as photons. The energy of a photon is equal to, it is a product of frequency and Planck's constant. E is equal to hf is equal to hc over lambda, where E, it denotes the energy of photon, H, it is Planck's constant, F, it denotes the frequency of light, C, it is the speed of light in vacuum, and lambda, it is the wavelength of light. This can be understood that different frequency of light, they carry photons of varying energy and vary wavelength. For example, the frequency of blue light, it is greater than red light, which means that the energy of blue light is greater than the red light. However, it also means that the wavelength of red light is greater than blue. Threshold energy for the photoelectric effect. For the photoelectric effect to occur, the photons that are incident on metal, they must carry some sufficient energy to overcome the attractive forces that bind the electron to the nuclei of the metals. This minimum energy that is required by the electron to break the bonds from the metal and to become free, this energy it is called as threshold energy, and it is denoted by hyphen. For a photon to possess energy equal to threshold energy, its frequency it must be equal to threshold frequency, and its wavelength it must be equal to threshold wavelength. The threshold frequency it usually denoted by the symbol FTH, and the associated wavelength it is denoted by the symbol lambda TH. The relationship between the threshold energy and the threshold frequency can be expressed as follows, where work function is equal to product of H and threshold frequency is equal to product of HC over threshold wavelength. The relationship between frequency of incident photon and the kinetic energy of emitted electrons. In photoelectric effect, the energy of incoming photon, it is completely changed in its kinetic energy. The relationship between the energy of the photon and the kinetic energy of the emitted photon, they can be written as energy of photon is equal to work function plus energy of the emitted electron, where E of photon, it donates the energy of the incident photon, which is equal to HF. Work function, it donates the threshold energy to the metal surface. It is equal to H multiplied by threshold frequency. Energy of electron, it donates the maximum kinetic energy of the photoelectron, which is equal to 1 over 2 mv square, where m it is the mass of one electron, which is equal to 9.1 multiplied by 10 raised power minus 31 kgs. If the energy of photon it is less than the threshold energy, then there would be no emission of photoelectrons. Thus, the photoelectric effect would not occur if threshold energy is greater than the energy of photon, and if the threshold frequency is greater than the frequency of the incoming photon. An illustration detailing the effect of frequency of the incident light on the kinetic energy of the photoelectron, it is provided below. This figure, it shows that from the image, it can be observed that the photoelectric effect does not occur when red light strikes the metallic surface, because the frequency of red light it is less than the threshold frequency. However, or in contrary, the photoelectric effect would occur when yellow light strikes the metal and the photoelectrons are emitted. The photoelectrons there also occur when blue light strikes the metal. However, the kinetic energy of the blue light would be greater than the electrons that are emitted from yellow light, because the energy of blue light is greater than that of yellow. It is important to note that the threshold energy it varies from metal to metal, which means that it is a material property. It is not a constant property. This is because the attractive force that binds the electron to the metal, they are different from metal to metal. It can also be noted that the photoelectric effect, it can also take place in non-metals, but the threshold frequency of metallic substances, they are very high. Experimental study of photoelectric effect. This diagram, it shows all the apparatus that are used in that experiment. The given experiment, it is used to study the photoelectric effect experimentally. In an evacuated glass tube, there are two zinc plates, which are abbreviated as C and D. Plate C, it acts as anode, and D acts as cathode or photosensitive plate. Two plates, they are connected to a battery and emitter. If the radiation they are incident on plate D, which is photosensitive, it releases electrons or it ejects out electrons, and a current flows in the circuit. This current is called as photoelectric current because it produced due to photoelectrons. Einstein's view about photoelectric effect. Consideration of these unexpected behavior, it led the greatest scientist at that time, Dr. Albert Einstein, to formulate in 1905 a new corpuscular theory of light, in which each particle of light or photon, they contain a fixed amount of energy or quanta that depends on light's frequency. It is similar to that of Planck's view, but he calls these discrete packets of energy as photons. However, Planck called them as quanta. In particular, a photon, it carries an energy E, which is equal to hf, where f it is the frequency of light and h it is Planck's constant. The electromagnetic radiation that are emitted from hot body. The relationship may also be written in equivalent from E is equal to 8c over lambda, where c it is the speed of light and lambda it is the wavelength. According to Einstein, each photon of energy E is equal to product of H and V, where V it shows the frequency of photon in hertz and H is Planck's constant. According to Einstein's explanation of photoelectric effect, the energy of photon it is equal to the threshold energy plus kinetic energy of the emitted electrons. Einstein's photoelectric equation, according to Einstein's theory of photoelectric effect, when a photon collides inelastically with electrons, the photon is absorbed completely or partially by the electrons. So if an electron in a metal, it absorbs a photon of energy, it uses the energy in the following ways. Some energy, it is used in making the surface of electron free from the metal. It is also known as work function of the material. The rest of the energy it is converted into the kinetic energy of emitted electrons. Einstein's photoelectric equation explains the following concepts. The frequency of the incident light it is directly proportional to its kinetic energy of the emitted electron. And the wavelength of incident light they are inversely proportional to kinetic energy of the electrons. The intensity of radiation or incident light it refers to the number of emitted electrons or the number of photons in the light beam. Greater the number of photon, greater would be the number of emitted electrons. More intensity, it means that more photon and vice versa. Intensity, it has nothing to do with the energy of photon. However, intensity do affects the current that flows in a circuit. The intensity of radiation is increased, the rate of emission increase, but there would be no change in the kinetic energy of emitted electron. With an increasing number of the emitted electron, the value of only photoelectric current increase. Photoelectric principle. According to quantum mechanics, electron bound to atom, they occur in specific electronic configuration. The highest energy configuration that is normally occupied by electrons by a giving material, it is known as valence band. And the degree which is filled largely determines the material's electrical conductivity. In a typical conductor or a metal, the valence band it is about half filled with electrons which are radially moved from atom to atom carrying a current. In a good insulator such as glass or rubber, the valence band is filled and the valence electron they have very little mobility, which means that they are not free. Like insulators, semiconductors they generally have their valence band filled, but unlike insulators, very little energy is required to break or to excite an electron from valence band to the next energy band. It is also which is also known as conduction band. Because an electron excited to this higher energy level, it is relatively free. For example, band gap of silicon, it is 1.12 electron volts, and that of gallium is 1.42 electron volt. It is in the range of the energy that is carried by photons of infrared and visible light, which means that silicon and germanium, they can also be used for photoelectric effect. They can raise electrons in semiconductor to the conduction band. Depending on how the semiconducting material is configured, this radiation may enhance its electrical conductivity by adding to an electric current already induced by an applied voltage. or it may generate a voltage that is independent of any external voltage source. Photoconductivity it arises from the electron freed by the light and from the flow of positive charge as well. Electrons raised to the conduction band, they correspond to missing negative charge in the valence band. This negative charge, they are typically called as holes. Both electrons and holes, they increase current flow when the semiconductor is illuminated, such as shown in the photovoltaic effect. The photovoltaic effect, a voltage is generated when the electrons freed by the incident light, they are separated from the holes that are produced. They are producing a difference in the electrical potential. It is typically done by using a PN junction rather than a pure semiconductor. A PN junction, it occurs at the junction between P-type and N-type materials or semiconductors. These opposite regions, they are created by the addition of different impurities to produce excess electrons in N-type or excess holes in P-type. Illumination-free electrons and holes on the opposite side of junction to produce a voltage cross the junction that can propel current, thereby converting light into electrical power. Other photoelectric effects are caused by radiation at higher frequencies, such as X-rays and gamma rays. These high-energy photons, they can never release the electron near the atomic nucleus because they have higher energies where they are tightly bound. When such an inner electron it is ejected, a higher energy outer electron it quickly drops to fill the vacancy. The excess energy result in the emission of one or more electrons from the atom, which is called as Auger effect. Also seen as high photon energies in the Compton effect, which arise when an X-ray or gamma ray photon it collides with an electron. This effect can be analyzed by some principle that governs the collision between any two bodies, such as uh, such as the collision between electron and X-ray, including the conservation of mass and charge and momentum. The photon loses energy to the electron. A decrease in the correspond to an increased photon wavelength according to Einstein relation E is equal to hc over lambda. Which means that when the X-ray collides with electron, that its energy decreases and the wavelength of the electron increase, which means that energy is converted into wavelength. Such that the electron and the photon part at the right angle to each other, the photon's wavelength increase by a characteristic amount called as Compton's wavelength, which is approximately equal to 2.43 multiplied by 10 raised power minus 12 meters. Now we will discuss the minimum condition for photoelectric effect, threshold frequency. What is threshold frequency? Threshold frequency, it is the minimum frequency at which the photoelectric effect occurs, or it is the minimum frequency of the incident light that will produce a photoelectric effect. It is constant for specific metal, but it may be different for different metals. If the threshold frequency is greater than the frequency of incident photon or light, then there would be no photoelectric effect. However, if both of them they are equal, then photoelectric effect would occur. However, the kinetic energy of the electron would be zero. It is because the energy, all the energy, it is used to break the bond between electron and that matter. If the energy or the frequency it is greater than threshold frequency, then the photoelectrons they will be emitted as well as the photoelectric effect would occur. Threshold wavelength. Threshold wavelength. It is the maximum value of wavelength at which the photoelectric effect would occur. For the wavelength that are above this threshold, there would be no photoelectrons emitted. If threshold wavelength it is less than the wavelength of incident light, then photoelectric effect will take place and the ejected electron they have kinetic energies. However, if both of them are same, then photoelectric effect would occur, but the kinetic energy of the photoelectron it would be zero. However, if the energy or if the wavelength of the incident light it is greater than threshold wavelength, then no photoelectric effect would occur. Work function or threshold energy. The minimum energy that is required by the electron to become free from the metal surface. It is called as threshold energy or work function. If work function is greater than energy, then no photoelectric effect would take place. However, if both of them they are equal, then photoelectric effect would take place, but the kinetic energy of the emitted electron would be zero. And if the energy is greater than threshold energy, the photoelectric effect would take place, as well as the emitted electron, they have some value of kinetic energy. The energy of the emitted or incoming ray. The energy of the incoming ray, it must be equal or less than 0.5 MeV. If it is greater, then the competence effect and the pair production would take place. Radiation that are used for photoelectric effect. There are different metals that show the phenomena of photoelectric effect. Most of them, they show this effect when a ray of specific energy it falls on them. It is probably due to their specific threshold frequency and work function. Sodium and potassium, they show this effect in the visible light, and all the other metals, they show this in UV region. Factors that affect the photoelectric effect. There are many factors that affect it. For example, the intensity of the incident radiation, the potential difference between the metal plate and the collector, the frequency of the incident radiation. The effect of intensity. In the following diagram, there show three values of the current. I3, it is greater than I2, it is greater than I1. As we discussed earlier, that intensity, it is directly proportional to current, which means that photon that have greater intensity or that light that have great number of photons, they have greater current as compared to those that have lower. However, can also be seen from the diagram that the stopping potential it is same.